There is a stretch of seafloor between Mexico and Guatemala, about 90 kilometers across, that produced almost every significant earthquake recorded anywhere on this planet this week. 2 days ago, a magnitude 7.3 ruptured there, and everything that followed looked like the textbook. A magnitude 6.0 aftershock at 30 minutes, a run of fives, a sequence settling into ordinary decay. Then last night it produced 8 more earthquakes in 9 hours, and its largest event yet arrived a full day after it was supposed to be fading. Tonight we walk through what an aftershock sequence is meant to do, why this one is not doing it, and the one measurement that would tell us whether that matters. Because the 2 agencies tracking this earthquake do not agree on that measurement, not slightly, by a factor of 3. Before we go any further, if you enjoy what we do here at Project Nightwatch, hit like and subscribe so you don't miss any of our nightly debriefs. Also, drop a comment and tell me where you're watching from. Let's get into it. Part 1. The night. The numbers stopped falling. 2 days ago, I told you this was normal. I want to start there because that is the honest place to start. On July 17th, a magnitude 7.3 earthquake tore open the seafloor along the Middle America Trench, off the coast of southern Mexico and Guatemala, and everything that happened in the hours afterward followed the script so precisely that you could have set your watch by it. A magnitude 6.0 aftershock arrived roughly 30 minutes later. A run of magnitude 5s followed through the afternoon and into the night. A magnitude 5.2 came in shortly after midnight. The tsunami threat was evaluated, measured at about half a foot and stood down. That is what a magnitude 7.3 is supposed to do. It ruptures, it rings, and then it settles. The expectation on the table was 1 or 2 more magnitude 6s over the following days, a gradual thinning of the sequence, and then a slow fade back into the ordinary background noise that this stretch of ocean floor produces every single week of the year. Then the sequence did something else. Across roughly 9 hours, spanning the evening of July 18th into the early hours of July 19th, that same patch of seafloor produced at least 8 earthquakes of magnitude 4.5 or greater. 3 of them came in at magnitude 5.3 or larger, and the biggest of them, a magnitude 5.7, did not arrive early in the sequence when the energy release should have been at its most vigorous. It arrived a full day after the sequence had already been assessed as decaying. Here is the number that made me sit up. Every week seismologists track the global count of earthquakes at magnitude 4.5 and above. It is one of the simplest and most useful measures of what the planet as a whole is doing. Over the 7-day window ending this morning, that global count rose from 137 to 144, 7 new earthquakes above magnitude 4.5 worldwide. And this one stretch of seafloor, a zone you could drive across in about an hour if it were on land, supplied essentially all of them. That is what I want you to hold on to as we go through this, because it reframes the entire question. This is not a story about one region being busy. For a stretch of hours last night, one small piece of the ocean floor between Mexico and Guatemala was doing almost all of the significant earthquake work happening anywhere on this planet. So the question in front of us is narrow, and I want to keep it narrow, because narrow questions are the ones you can actually answer. The question is not whether a bigger earthquake is coming. Nobody on Earth can answer that, and anyone who tells you otherwise is selling something. The question is this: is this sequence still decaying? Let me give you the events, because the pattern only becomes visible when you lay them out in order. At 17:26 on July 18th, Universal Time, a magnitude 5.7 struck approximately 72 kilometers southwest of Puerto Madero, Mexico. 14.3 degrees north, 92.8 degrees west. Green alert level, no tsunami flag. 5.5 hours later, at 22:49, a magnitude 4.6, slightly to the northwest. 49 minutes after that, at 23:38, a magnitude 4.5, this one to the east, about 39 kilometers west-southwest of a coastal town called Brisas Barra de Suchiate. Then a gap. 2 hours of relative quiet, which is exactly what you would expect from a sequence winding down. And then, at 1:47 on the morning of July 19th, a magnitude 5.3 to the south of everything that came before it. 14 minutes later, at 2:01, a magnitude 4.6. 17 minutes after that, at 2:18, another magnitude 5.3. 3 significant earthquakes inside 31 minutes after a 2-hour lull on the second day of a sequence that was supposed to be fading, and that is only the catalogued events at magnitude 4.5 and above. Add in the additional entries that appeared in the survey's own listings for the same zone, another magnitude 5.3 and another magnitude 4.6, and add in the observations from the ground that night, which independently logged a magnitude 4.7 earlier that evening and a magnitude 4.4 earlier that morning, and the picture stops being a list and starts being a swarm. Someone watching a three-dimensional globe display that night described what he was seeing as a pancake of aftershocks. That is a good description, and I want to unpack why it is a good description, because the shape of this thing matters as much as the count. The catalogued epicenters spread from about 14.15 degrees north to about 14.44 degrees north, and from about 92.54 degrees west to about 93.31 degrees west. Translate that out of coordinates and into distance, and you get a zone roughly 32 kilometers across from north to south, and roughly 83 kilometers across from east to west. Call it 90 kilometers at its longest dimension. That is a broad footprint. Not enormous by the standards of a magnitude 7.3 rupture, but broad enough that these earthquakes are not all happening on the same small patch of rock. They are distributed, they are spread across a surface, and they are spread in a way that will matter enormously when we get to the part of this story where two of the world's best earthquake monitoring agencies look at the same event and give you two different answers. Now, before anyone gets ahead of me here, I want to be clear about something, and I am going to keep being clear about it throughout. Vigorous aftershock sequences are not rare. Subduction zones are the most productive earthquake environments on the planet, and a magnitude 7.3 on a subduction interface can and routinely does generate dozens of magnitude 4 and magnitude 5 events over the course of a week or more. Aftershock decay is a statistical process, not a smooth curve. Real sequences are lumpy. They cluster. They go quiet for 6 hours and then produce 3 events in half an hour, exactly like this one did, and that is entirely within the range of ordinary behavior. So the most likely explanation for everything I have just described is the boring one. Large earthquake, energetic consequences, everything eventually settles. But there is a reason I am spending 2 hours on this rather than a paragraph, and the reason is that a specific checkable prediction was made about this sequence in public less than 48 hours ago, and parts of that prediction have not held up. The prediction was that the sequence looked entirely typical and would produce 1 or 2 more magnitude 6s as it wound down. What actually happened is that no magnitude 6 has appeared at all in this burst, and instead the sequence produced its largest event yet a full day into what should have been its decline. That is not a catastrophic failure of the forecast. It is a small one. But small failures in a system this well understood are exactly the kind of thing worth looking at closely, because they usually mean one of 2 things. Either the sequence is behaving in an unusual but ultimately harmless way, or the model we are using to describe it has the wrong picture of what is actually breaking down there. And that second possibility is where this gets genuinely interesting, because it turns out we cannot currently tell which one it is. The single measurement that would resolve it is the one measurement the instruments are arguing about. Before I get to that, one piece of housekeeping, because if you go looking at the raw catalogues yourself tonight, you're going to run into something confusing, and I would rather you hear the explanation from me. If you pull the standard 7-day listing of earthquakes at magnitude 4.5 and above, you may find that the largest event in it is that magnitude 5.7, with no sign of the magnitude 7.3 anywhere. That looks like a contradiction. It is not. It is a display limit. These feeds routinely return only the most recent 20 or 30 entries out of a total that runs into the hundreds, and the July 17th main shock has simply scrolled off the end of the return slice. It is still in the catalogue. It is just not in the window you happen to be looking through. I mention it because that kind of thing generates an enormous amount of confusion and occasionally accusations. Somebody notices a large earthquake missing from a feed and concludes it was removed. In almost every case, the earthquake was never deleted. The list was simply truncated, exactly as it was designed to be, and nobody thought to explain that in the interface. So the sequence, in full, is a magnitude 7.3 on July 17th, followed by a magnitude 6.0 half an hour later, followed by a run of magnitude 5s through that night, followed by what should have been decay, followed instead by the burst we have just walked through. Now I need to give you the rulebook, because you cannot judge whether something is breaking the rules until you know what the rules actually say. Part 2. What aftershocks are supposed to do. There are two laws that govern how aftershocks behave, and both of them are old enough to have grandchildren. The first is called Omori's Law, and it dates back to 1894. A Japanese seismologist named Fusakichi Omori noticed that after a large earthquake, the rate of smaller earthquakes in the same area did not fall off randomly. It fell off in a very specific mathematical shape. The number of aftershocks per day decreases roughly in proportion to 1 divided by the time elapsed since the main shock. Strip out the mathematics, and what that means in practice is something you can hold in your head. Whatever the aftershock rate was on day 1, on day 2 you get about half of it. On day 4, about a quarter. On day 10, about a tenth. The sequence does not stop exactly. It thins. It stretches out. Aftershock sequences from genuinely large earthquakes can technically continue for decades, ticking along at a rate so low it becomes indistinguishable from the ordinary background. This law is remarkable for how well it works. It was formulated more than a century ago, before plate tectonics was understood, before anyone knew what a subduction zone was, and it still holds today across almost every tectonic environment on Earth. When forecast agencies publish aftershock probability tables after a major earthquake, telling you there is a certain percent chance of a magnitude 6 in the next week, Omori's Law is doing most of the work behind those numbers. The second rule is called Both's Law, named after the Swedish seismologist Marcus Both. It is simpler. It says that the largest aftershock in a sequence tends to be about 1.2 magnitude units smaller than the main shock. Run that for our earthquake. Main shock magnitude 7.3, subtract 1.2. That predicts a largest aftershock somewhere around magnitude 6.1. And what did we actually get? A magnitude 6.0, roughly 30 minutes after the main shock. That is a near-perfect fit. If you were grading this sequence on its first afternoon, you would have given it full marks. The main shock behaved. The largest aftershock behaved. The timing behaved. Everything about July 17th was textbook, and the assessment that it was a typical sequence was completely reasonable, given the data available at the time. Which brings us to why the last 24 hours stand out. Under Omori's Law, day 2 should be quieter than day 1, noticeably quieter, and within day 2 the rate should be gently declining rather than holding steady or climbing. What the catalogue actually shows is a cluster of at least 8 significant events concentrated in a single 9-hour window on day 2, including the sequence's largest event to date. Now, I want to be scrupulously careful here, because this is exactly the point where a channel that wanted to scare you would tell you the laws have been broken and something unprecedented is happening. That is not what I am telling you. Omori's Law describes an average rate, not a schedule. Aftershock sequences fluctuate around that average constantly, and the fluctuations can be large. A sequence can produce a quiet period and then a burst, and the burst can contain the sequence's largest event, and none of that violates anything. Both's Law has genuine scatter around it as well. Some sequences produce largest aftershocks 2 full magnitude units below the main shock. Others produce largest aftershocks only a few tenths below, and a handful of sequences in the historical record have produced an aftershock larger than the original event, at which point seismologists simply relabel which one was the main shock and move on. So no law has been violated. What has happened is milder and more interesting than that. The sequence is running on the energetic side of expectation. It is inside the envelope, but it is not sitting in the middle of the envelope. Let me give you a sense of scale so the magnitudes are not just abstract numbers, because I think this is where most coverage loses people. The magnitude scale is logarithmic, which everyone says and almost nobody unpacks. Each whole step up is about a 32-fold increase in energy released. So a magnitude 6 is not slightly bigger than a magnitude 5. It is 32 times bigger in terms of energy. A magnitude 7 is roughly 1,000 times the energy of a magnitude 5. And our main shock, at magnitude 7.3, released somewhere in the region of 1,000 times the energy of each of those magnitude 5.3 events that came through last night. Which tells you something important about what an aftershock sequence actually is. It is not the earthquake continuing. The earthquake is over. It happened in about 20 or 30 seconds along a fault surface tens of kilometers long, and in that time it released the overwhelming majority of the strain energy that had been stored in that patch of crust over decades or centuries. What follows is the cleanup. When a fault slips, it does not just release stress, it redistributes it. The rock around the edges of the ruptured patch, the rock at the ends, the rock above and below on adjacent structures, All of it experiences a sudden change in the forces acting on it. Some of that rock was already close to its breaking point. The change is enough to push it over, so it breaks in a much smaller way, and that breakage redistributes stress again, and so on outward and downward, in a cascade that gradually exhausts itself. That cascade is what Amori's law describes, and the reason the shape of the cascade matters is that its geometry tells you about the geometry of what broke. A tight, compact aftershock cloud that stays close to the main shock and fades quickly suggests a clean rupture on a single fault surface that has fully relieved itself. A broad, spread-out cloud that keeps generating significant events on day 2 and day 3 suggests something more complicated. It suggests that the stress redistribution reached structures that were closer to failure than anyone realized, or that more than one fault system is involved. Our sequence is the second kind, 90 kilometers of spread, events on day 2 rivaling the events on day 1, and a depth distribution that is frankly all over the place. Let me put those depths in front of you, in kilometers, exactly as catalogued. 10, 10, 10, 16, 16, 18, 19.6, 29, 29, 35, 35. Look at the range there. The shallowest events are sitting at 10 kilometers below the seafloor. The far end of the distribution sits at 35 kilometers. That is a spread of 25 kilometers of vertical distance across a single earthquake sequence in a single 90-kilometer zone. In a lot of tectonic settings, a spread like that would be strange enough on its own to warrant a second look. In a subduction zone, it is more than strange. It is potentially diagnostic, because at a subduction zone, the difference between 10 kilometers and 35 kilometers is not a detail. It is the difference between two completely separate populations of earthquakes, generated by two completely different physical processes that happen to occupy the same spot on a map. And when I went to check which of those two populations this sequence belongs to, I found something I did not expect. Part 3. The two depths. Two agencies track this earthquake, the United States Geological Survey and the European Mediterranean Seismological Center. Both are excellent. Both are staffed by serious people using serious instruments. Both published a solution for the magnitude 5.7 that struck on the evening of July 18th. The survey says that earthquake occurred at a depth of 10 kilometers. The European Center says it occurred at a depth of 29 kilometers. Same earthquake, same moment. Nearly a factor of 3 between the two answers. Now, if you have never spent time inside earthquake catalogues, your first instinct might be that somebody made a mistake. Your second instinct might be something less charitable than that. Both instincts are wrong, and the real explanation is far more interesting than either, so let me walk you through why this happens. Locating an earthquake means solving for 4 things at once: latitude, longitude, origin time, and depth. You solve for them using the arrival times of seismic waves at stations spread across the surface. Different wave types travel at different speeds, so the gap between when the fast waves arrive and when the slow waves arrive tells you how far away the source was. Combine a lot of stations and you triangulate. 3 of those 4 parameters are usually well constrained. Latitude, longitude, and origin time fall out of the geometry reliably, provided you have stations in enough directions. Depth is different. Depth is hard, and it is hard for a specific structural reason. To pin down how far below the surface an earthquake occurred, you want stations directly above it or very close to it, and you want to catch the waves that bounce off the surface and come back down. The delay between the direct arrival and the surface reflected arrival is what gives you depth with any precision. Now think about where this earthquake happened. 80 kilometers out to sea from the coast of Chiapas. There are no seismometers out there. Every station recording this event is on land, which means every station is on one side of it. The geometry is one-sided. The surface reflected faces are weak or ambiguous, and the depth solution becomes the softest number in the entire calculation. This is so well known that catalogues have a convention for it. When a depth solution will not converge, the software often fixes depth at a default value and solves for everything else. That default is very frequently 10 kilometers, which is why, when you look at the list I read you a moment ago, you see 10 kilometers appearing again and again and again. Some of those 10s are measurements. Some of them are almost certainly placeholders, meaning nothing more than the honest statement that the depth could not be determined from the available data. Several of these events remain under automatic status, meaning no human seismologist has reviewed the machine solution yet. Those depths will move. Some of them will move a lot. So the disagreement between the two agencies is not evidence that anyone is hiding anything. It is evidence that measuring the depth of an offshore earthquake is genuinely, technically difficult, and that two teams using different velocity models and different station sets arrived at different answers to a hard question, and then both published their answers openly for anyone to check. But here is why I have spent this long on what sounds like a technical footnote. At a subduction zone, two entirely distinct families of earthquakes exist in the same place at different depths, and depth is essentially the only thing that separates them. The first family lives on what is called the interface. This is the contact surface where one tectonic plate slides beneath another, the seam between them, the place where they are physically pressed together and locked by friction, over an area that can be thousands of square kilometers. When that seam fails, it produces what we call a megathrust earthquake. These are the largest earthquakes the planet is capable of generating. Every earthquake in recorded history above magnitude 9 has been a megathrust earthquake. They are also the ones that displace enormous volumes of seawater and produce the tsunamis that kill people hundreds of kilometers away. The second family lives inside the descending plate itself, below the interface. As a slab of oceanic crust bends downward and sinks into the mantle, it experiences enormous internal stresses. It is being pulled down by its own weight, bent around a corner, heated and compressed. It cracks internally. Those cracks are earthquakes too. They are called intraslab events, and they are usually the opposite type of faulting from megathrust events. Where a megathrust is compressional, with the plates being shoved together, an intraslab event is often extensional, with the slab pulling itself apart under its own weight. Intraslab earthquakes can be large and they can be deadly, particularly because they often occur beneath the coastline rather than offshore. But they are a different process, on a different fault population, obeying different rules. Here is the part that matters for tonight. Foreshock sequences, the pattern where a series of moderate earthquakes precedes a much larger one, are associated primarily with the locked interface. That makes physical sense. A locked megathrust is a surface that has been accumulating strain for a very long time, held in place by friction, sitting somewhere near its failure threshold across an enormous area. Small failures near the edges of that locked patch can plausibly cascade into a large one. Intraslab sequences generally do not do this. The slab cracks internally, releases, and stops. It is not a system that is primed across a wide area waiting for a trigger. So the question of which family this sequence belongs to is, without exaggeration, the whole question. If these earthquakes are happening at 10 to 16 kilometers, on or near the interface, then we are watching a locked megathrust behave in a somewhat unusual way, and that is a situation worth monitoring carefully. If they are happening at 29 to 35 kilometers, inside the slab, then we are watching a cracking plate do what cracking plates do, and it is far less consequential. And the answer, right now, tonight, is that we do not know, because the depths scatter across both ranges, and the largest event in the burst has two published solutions that land on opposite sides of the line. I want to sit with that for a second, because I think it is the single most honest and most unsettling thing in this entire story, and it has nothing to do with fear. We have an extraordinary machine for watching this planet. Thousands of seismometers on every continent, satellites measuring ground deformation to the millimeter, catalogues updated within minutes of an event, all of it published in the open for anyone with an internet connection. It is one of the genuine achievements of modern science, and I do not think people appreciate how good it is. And that machine, pointed at an active earthquake sequence 80 kilometers off a populated coastline, currently cannot tell us the one number we would need in order to know what we are looking at. Not because anyone is hiding it, not because anyone is incompetent, because the water is in the way and the instruments are all on one side, and physics is under no obligation to make itself convenient. That is the situation. Now let me show you what is actually down there, because the machine that built this trench has been running for a very long time, and its output is not subtle. Part 4. 76 millimeters a year. Hold your hands about 3 inches apart. That is roughly how far the Cocos Plate travels every year as it drives itself underneath North America. 76 millimeters per year, heading northeast, according to the United States Geological Survey. Independent regional observers who watch this boundary closely tend to cite an average nearer 88 millimeters per year. Either number is fast. In the world of plate tectonics, where most boundaries creep along at the speed your fingernails grow, this is one of the quicker convergent margins on the planet. I want to spend some time on this because I think the mechanics are the part that most coverage skips, and without the mechanics, the earthquakes are just numbers on a map. The Cocos Plate is a piece of oceanic crust sitting in the eastern Pacific. It is young, geologically speaking, born at a spreading ridge to its west where new seafloor is continuously manufactured. It is also relatively small, and it is being consumed from the east faster than most plates its size. That consumption happens at the Middle America Trench, a curved gash in the seafloor running from central Mexico down past Guatemala, El Salvador, Nicaragua, and Costa Rica. At that trench, the Cocos Plate bends downward and slides beneath the North American Plate. This is subduction, and the reason it happens is simply density. Oceanic crust is basaltic and heavy. Continental crust is granitic and comparatively light. Where the two meet head-on, the heavy one goes under, but it does not go under smoothly. If it went under smoothly, there would be no earthquakes at all, and the entire margin would just be a slow, silent, grinding conveyor belt. Instead, the two plates weld themselves together by friction across the contact surface, and they stay welded while the deeper parts of the system keep moving. That is the crucial image, and it is worth being precise about. Deep beneath the trench, well below the depths where rock is cold and brittle, the slab is descending continuously. It never stops. There is no pause. But near the surface, across a band of the contact surface that might extend from a few kilometers below the seafloor down to 40 or 50 kilometers, the rock is cold enough and the pressure is right for the two plates to lock together and refuse to slip, so you have a system where one part is moving continuously and another part is stuck. The result is that strain accumulates. The overriding plate gets dragged downward and squeezed landward, elastically, like a diving board being slowly bent by someone walking out along it. Satellite measurements pick this up directly. You can watch coastlines contract toward the trench over years and decades, millimeter by millimeter, and then the friction gives way, the locked patch slips all at once, the bent diving board springs back, and everything that was compressed over a century releases in about half a minute. That is a megathrust earthquake. And that is what appears to have happened on July 17th, a reverse thrust rupture on, or very near the interface between the Cocos and North American plates. Now apply the arithmetic. 76 millimeters per year does not sound like much, but run it out. Over 10 years, that is 760 millimeters, more than 2 feet of accumulated relative motion. Over a century, 7.5 meters. Over 200 years, 15 meters. If a section of the interface has been locked for 2 centuries, then when it finally lets go, it has to make up 15 meters of motion in one event. That is where the energy comes from. It is not stored in the earthquake. It is stored in the deformation of an entire coastal region, accumulated 1 fingernail width at a time, for generations, and then discharged in seconds. This is also why the size of the rupture patch controls the size of the earthquake more than anything else. Magnitude scales with the area of the fault that slips, multiplied by how far it slips. A magnitude 7.3 probably ruptured something on the order of 50 to 80 kilometers of fault length with a few meters of slip. A magnitude 8 would need several hundred kilometers. A magnitude 9 needs something close to 1,000 kilometers of interface failing in a single coordinated cascade, which is why they only happen on the longest, straightest subduction margins on Earth. The Middle America Trench is capable of exceeding magnitude 8. That is not speculation. It has done it, in living memory, and we will get to that shortly. There is one more property of the Cocos Plate worth knowing, because it shapes how this whole system behaves, and that is its age. Oceanic crust gets older the further it travels from the ridge where it was born, and as it ages it cools, thickens, and becomes denser. Old oceanic crust is heavy and sinks steeply. The Pacific Plate entering the Mariana Trench is around 180 million years old, some of the oldest seafloor on Earth, and it plunges nearly vertically into the mantle. The Cocos Plate is young. Much of what enters the Middle America Trench is on the order of 10 to 25 million years old. Young crust is warmer, more buoyant, and more reluctant to sink. It resists. And when a plate resists going down while the forces behind it keep pushing, the two plates press together harder across the contact surface. That has consequences you can measure. Subduction zones consuming young, buoyant crust tend to have shallower slab angles, broader locked zones, and stronger mechanical coupling between the plates. Broader coupling means larger potential rupture areas, and larger rupture areas mean larger available magnitudes. It is one of the reasons this margin behaves the way it does, and it is a useful corrective to the intuition that older and heavier means more dangerous. In subduction, the young and stubborn plates are frequently the ones that produce the biggest earthquakes, because they are the ones that grip hardest before they let go. But before we do, I want to point out something about the geography of where this sequence is happening, because the location is not arbitrary. The earthquakes we have been discussing are clustered off the coast of Chiapas, close to the border between Mexico and Guatemala. Look at a plate map of that region, and you will notice it is unusually crowded. This is not a simple two-plate boundary, it is a junction. The Cocos Plate is subducting from the southwest, the North American Plate sits to the northwest, and the Caribbean Plate sits to the southeast, meeting North America along a boundary that runs east from Guatemala out into the sea. 3 plates, 1 corner, and our earthquake sequence is sitting more or less on top of it. Plate junctions are messy. The clean geometry of a two-plate boundary breaks down. Faults intersect at awkward angles, stress fields rotate over short distances, and the simple models that work well along the middle of a margin start to lose their grip. When you see an earthquake sequence spread across 90 kilometers, with depth scattering across 25 kilometers of vertical range, one entirely plausible explanation is simply that it is happening in a structurally complicated place where more than one fault system is available to break. That is the mundane reading, and it may well be the right one. But it also means that stress released here has more than one place to go, and that is going to become the central question of the second half of this video, because within hours of last night's burst, moderate earthquakes started appearing to the east, on that Caribbean boundary, hundreds and then thousands of kilometers away. Before we follow that thread, though, we need to talk about the last time this particular stretch of the trench did something dramatic. Because there is an event in the recent history of this exact region that everyone reaches for as a comparison, and almost everyone reaches for it incorrectly. Part 5. The Ghost of September 8th. On the 8th of September 2017, at just before midnight local time, an earthquake struck off the coast of Chiapas that was so large it remains to this day the strongest earthquake recorded in Mexico in over a century. Magnitude 8.2. It killed approximately 98 people. It generated a tsunami. It was felt by tens of millions across Mexico and Central America. Buildings came down in Yucatan and in Oaxaca and in the towns along that coast. It is remembered as the Tehuantepec earthquake, and if you were anywhere in southern Mexico that night, you have not forgotten it. It happened almost exactly where last night's earthquakes are happening. So the obvious move, the one that writes itself, is to say that this same stretch of fault produced a magnitude 8.29 years ago, and now it is swarming again, and therefore we should all be watching for another one. I am not going to make that move, because when you look at the mechanics, the comparison is more complicated than that, and the complication is genuinely important. The 2017 Tehuantepec earthquake was not a megathrust event. It was an intraslab event, a normal faulting rupture inside the descending Cocos Plate itself at a depth of approximately 70 kilometers. The slab did not fail against the overriding plate. The slab tore itself apart internally under the tension created by its own sinking weight. That distinction is not academic. It changes what the event tells us about the interface above it. Think about what has to happen for a slab to break like that. The Cocos Plate enters the trench, bends downward, and begins to sink. As it goes, the leading part of the slab, now dense and cold and hanging in hotter mantle, is pulled downward by gravity. That pull is called slab pull, and it is one of the primary engines driving plate motion across the entire planet. But the slab is a solid sheet of rock, and if the front of it is being pulled down harder than the back of it is being fed in, the sheet goes into tension. It stretches, and eventually somewhere along its length it fractures. That is what happened in 2017, not the seam between two plates failing, the plate itself ripping. And here is the consequence that matters for tonight. Because the 2017 rupture happened inside the slab rather than on the interface, it did not release the strain accumulated on the locked interface above it. The megathrust in that region did not go in 2017. Whatever had been accumulating on that contact surface at 76 or 88 millimeters per year, was still there on the 9th of September 2017, and to a first approximation it is still there today, plus 9 additional years of loading. So when people invoke 2017 as the precedent, they are usually invoking it to say the region has released a lot of energy recently and might be quieter now. The mechanics suggest closer to the opposite. The region demonstrated that it can produce a magnitude 8.2, but it produced that magnitude 8.2 through a mechanism that left the interface question open. Now, I want to immediately balance that, because I can feel this tipping in an alarming direction and it does not deserve to. The presence of accumulated strain on a locked interface is not news. It is the permanent condition of every subduction zone on Earth. Cascadia has been accumulating strain since 1700. The Nankai Trough off Japan has been accumulating since 1946. The Chilean margin, the Alaskan margin, the Sumatran margin, all of them are loaded, all of the time, everywhere. That is what a subduction zone is. Saying that the Middle America Trench has strain stored on its interface is like saying a river has water in it. The question is never whether strain exists. The question is only ever whether something has changed about how close a particular patch is to releasing it, and that is the question nobody can currently answer. What the historical record does tell us is what this segment is capable of. Within 155 miles of the July 17th epicenter, there have been 7 earthquakes of magnitude 7 or greater since 1950. That is roughly 1 every 11 years. This is a busy, productive segment with a well-documented capacity for large events, and the largest of them was that 2017 intraslab rupture. I also want to flag one detail about the 2017 event that connects directly to what we discussed a few minutes ago. The Tehuantepec earthquake occurred at approximately 70 kilometers depth. Our current sequence is catalogued between 10 and 35 kilometers. That is a substantial vertical separation. 2017 was much further down, well inside the slab, in a regime where the plate is already committed to its descent. The current sequence sits in the depth band where you would expect interface and shallow intraslab events to coexist and be difficult to distinguish, which is exactly the ambiguity we ran into. There is one more thing about 2017 that I think about a lot, and it is not seismological. It is about how we talk about these events afterward. In the days after the Tehuantepec earthquake, there was a great deal of discussion about whether it had loaded or unloaded neighbouring faults, whether it made the next one more or less likely, whether the pattern of aftershocks was revealing something. Some of that discussion was rigorous, a lot of it was not, and 9 years later, the honest summary is that the region did what it always does. It kept producing earthquakes. It has produced hundreds of magnitude 4 and 5 events in the intervening years that nobody outside of seismology ever heard about because they did not damage anything and did not make the news. That is the baseline. That is the thing this current sequence has to be measured against. Not against a mental image of a quiet coastline that suddenly started shaking, but against a stretch of seafloor that shakes constantly and has shaken constantly for as long as we have been measuring. Against that baseline, is this sequence unusual? Somewhat. Is it unprecedented? No, but there is a threshold that would change that answer, and it was named out loud on a live stream by someone watching the globe at 11 o'clock at night. And it is the most useful thing anyone has said about this sequence so far. Part 6. The number that changes everything. Here is what was said, in substance, on the night of July 18th, by an observer watching this sequence unfold in real time. As of right now, this looks normal, but we need to watch the magnitudes. If we start seeing them kick up with multiple magnitude 6.0 earthquakes or above, that is a sign of further major earthquake potential out there, a major stress reliever, so to speak. This trench can produce earthquakes in excess of magnitude 8. I want to take that seriously, and I want to explain why it is a genuinely good piece of analysis, because it does something that most earthquake commentary never does. It states a threshold in advance. That is the difference between analysis and vibes. Anyone can look at a cluster of dots on a globe and say it feels ominous. What is far more useful is to say, here is the specific observation that would change my assessment, and here is the specific observation that would not. Because then you can check. The world runs its experiment, and you find out whether you were right. So let me be precise about where we stand against that threshold, as of the most recent data available to me. No magnitude 6.0 has occurred in the July 18th to 19th burst. The largest event in that burst is a magnitude 5.7, The next largest are two events at magnitude 5.3. The magnitude 6.0 that appeared in this sequence arrived 30 minutes after the main shock on July 17th, and that one fits Both's law almost exactly, meaning it is the expected largest aftershock rather than an escalation. The threshold has not been crossed. That is the current honest answer, and if you take nothing else away from this video, take that. Now let me explain why that particular threshold is the right one to watch, because the reasoning behind it is sound, and it connects to something genuinely unsettling about the limits of earthquake science. Foreshocks are only identifiable in retrospect. I want to say that again, because it is the load-bearing sentence of this entire video, and once you understand it, you will never look at earthquake news the same way. A foreshock is not a category of earthquake with distinguishing physical properties. There is no measurement you can take on an earthquake that tells you it is a foreshock. A foreshock is simply an earthquake that happened to be followed by a bigger one. The label is applied afterward, retroactively, by historians of the sequence. Roughly 5 to 10% of moderate earthquakes end up being reclassified as foreshocks because something larger followed them within days, which means that 90 to 95% of the time, a moderate earthquake is just a moderate earthquake. Those odds strongly favour calm. But run the statistic the other way, and it becomes less comfortable. A substantial fraction of large subduction earthquakes are preceded by foreshock activity. Both of those statements are true simultaneously, and together they produce a situation that is close to operationally useless. Most swarms are nothing. A meaningful share of large earthquakes announce themselves, and there is no reliable way to tell in the moment which situation you're in. The clearest illustration of this is the 11th of March 2011. 2 days before the magnitude 9.0 Tohoku earthquake devastated northeastern Japan, a magnitude 7.3 struck off the Sanriku coast. At the time, it was treated as what it appeared to be, a significant earthquake with its own ordinary aftershock sequence. Japanese authorities did what any competent authority would do. They monitored it, they issued the standard advisories, and they watched the aftershocks decay along a perfectly normal curve. 2 days later, a section of the Japan Trench roughly 500 kilometers long failed in a single rupture. The seafloor lurched dozens of meters, and a tsunami killed nearly 20,000 people. Only afterward was that magnitude 7.3 reclassified as a foreshock. Nobody made a mistake. This is the part people get wrong when they revisit that history looking for someone to blame. The Japanese monitoring system is arguably the best in the world. The scientists watching it were not careless. They applied the correct statistical treatment to the information available, and the correct statistical treatment said this is a large earthquake with an ordinary aftershock sequence, because that is what it looked like, and that is what the overwhelming majority of such sequences turn out to be. The treatment was right. The outcome was catastrophic. Those two things can both be true, and the reason they can both be true is that we are dealing with probabilities, not predictions. So when someone says, watch for multiple magnitude 6s, they are not predicting anything. They are identifying the one pattern that would shift the probability meaningfully. Because a sequence that starts escalating in magnitude rather than declining is behaving in the way that the minority of foreshock sequences behave. It would not prove anything. It would not tell you when, or where, or whether. But it would move the odds, and moving the odds is the most that anyone honest can offer. And that pattern has not appeared. What has appeared is a sequence running slightly hot on rate, while its maximum magnitude stays flat. 8 events above 4.5, 3 above 5.3, top magnitude 5.7, holding steady across the burst rather than climbing. Rate is elevated. Magnitude is not escalating. That combination is much more consistent with a productive aftershock sequence in a structurally complicated junction than with anything more concerning, and I think that is the fairest reading of the data as it stands tonight. Let me add one more layer, because there is a piece of context that makes the current numbers feel smaller rather than larger. The Middle America Trench produces magnitude 4 and 5 earthquakes constantly, not occasionally, constantly. If you pull a year of data for this region, you will find hundreds of them, the overwhelming majority of which never appear in any news coverage anywhere in the world. The reason last night's cluster registers as remarkable is partly that it was genuinely concentrated in time, and partly that we are all looking at this region right now because a magnitude 7.3 happened here 2 days ago. Attention is not evidence. When we point our collective attention at a patch of the planet, we start noticing things that were always there. That is a real effect, and it accounts for a lot of what feels like escalation in earthquake coverage generally. But it does not account for all of it here, and I want to be fair in both directions. The concentration of 8 significant events into 9 hours is a real signal, not an artifact of attention. The global count going from 137 to 144 on the strength of one region is a real signal. The largest event of the burst arriving on day 2 rather than day 1 is a real signal. Real signals that do not yet mean anything definite. That is where we are. There is one more piece of context that belongs here, and it concerns how these forecasts are actually produced, because I think people imagine something far more mysterious than what happens. After a significant earthquake, the survey publishes an aftershock forecast. It is not a prediction, and it does not pretend to be. It is a probability table. It will tell you something like, over the next week, there is a certain percent chance of one or more earthquakes of magnitude 5 or above, a smaller percent chance of magnitude 6 or above, and a very small percent chance of something larger than the main shock itself. Those numbers update daily as the sequence evolves. The engine behind those tables is essentially the two laws we just covered, Omori and Both, combined with a third relationship called the Gutenberg-Richter law, which describes how many small earthquakes you get for every large one. Roughly speaking, for every magnitude 6 you get about 10 magnitude 5s, about 100 magnitude 4s, about 1,000 magnitude 3s. That ratio is remarkably stable across regions and across time. Run those three relationships together, and you can generate a forecast for any sequence within minutes of the main shock. It is transparent, it is published, and it is checkable. Which is why I keep saying that nothing about this situation is being hidden. Anyone can go and read the current probabilities for this sequence. The uncertainty we have been discussing is not concealed uncertainty. It is published uncertainty, expressed in percentages, by an agency that will tell you plainly that it cannot predict earthquakes. Which leaves one obvious question hanging, and it is the question that took this from a local story to something wider. If the stress released by the July 17th rupture went somewhere, where did it go? Because last night, while everyone was watching Chiapas, earthquakes started appearing to the east. Part 7. The stress went east. At around 8 minutes past midnight, Universal Time on July 19th, a magnitude 5.1 earthquake struck 149 kilometers south of Georgetown, in the Cayman Islands, depth 10 kilometers. About half an hour before that, at 23:31 on July 18th, a magnitude 4.7 struck near the Pacific coast of Nicaragua, roughly 80 kilometers southwest of Masachapa. The observer watching the globe that night noticed both, and connected them explicitly to what was happening in Chiapas. His reading, in substance, was this. One thing he had noticed since the magnitude 7.3 struck was increasing pressurization to the east along the plate boundary. What often takes place at the Middle America Trench is that a large event further pressurizes the region to the east, and that stress transfers inland to the Caribbean plate. The Cayman Islands earthquake looked to him like exactly that, and his conclusion was that the Caribbean plate needed watching. I want to take this apart carefully, because it contains something true, something plausible, and something that almost certainly is not what it appears to be, and separating those three is the useful work. Let me start with the physics, because there is a real mechanism here, and it deserves to be explained properly rather than hand-waved. When a fault slips, it changes the stress state of the rock around it. This is not controversial, and it is not speculative. It is measurable, it is modelled routinely, and it goes by the name of Coulomb stress transfer. The idea is that any fault has a certain amount of stress pushing it toward failure and a certain amount of friction holding it back. Slip on a nearby fault changes both of those quantities. In some directions from the rupture, the change pushes neighbouring faults closer to failure. In other directions, it pulls them further away, and those regions actually become quieter for a while, which is a phenomenon called a stress shadow. This works. It has been used to explain the migration of earthquake sequences along the North Anatolian Fault in Turkey through the 20th century, where a series of large earthquakes stepped progressively westward toward Istanbul over decades in a pattern that Coulomb modelling reproduces well. But Coulomb stress transfer has a range limit, and the limit is not vague. The effect scales down extremely rapidly with distance. As a working rule, meaningful static stress change extends about 1 to 2 fault lengths from the rupture. Our main shock at magnitude 7.3 likely ruptured something on the order of 50 to 80 kilometers of fault. 1 to 2 fault lengths is therefore somewhere between 50 and 160 kilometers. Be generous and call it 200 kilometers. The Nicaragua earthquake is roughly 700 kilometers away. That is already outside the generous estimate, though it sits on the same continuous subduction system, which means the two events share a common driving mechanism even if one did not directly cause the other. The Cayman Islands earthquake is roughly 2,000 kilometers away. Static stress transfer from a magnitude 7.3 at 2,000 kilometers is, for practical purposes, zero. Not small, not marginal, zero to any level of precision that matters. The stress change from that rupture at Cayman Island distances is smaller than the stress change caused by the tides, smaller than the change caused by a passing weather system, smaller than the seasonal loading of groundwater. It is lost in the noise many times over, so static transfer cannot be the explanation. But there is a second mechanism, and this one does reach. Dynamic triggering is caused by the seismic waves themselves. When a large earthquake occurs, it sends waves outward through the entire planet. Those waves carry stress with them, transiently as they pass. And in some cases, that transient stress is enough to push a fault that was already right at the edge of failure over the line. Dynamic triggering is real. The clearest demonstration came from the 1992 Landers earthquake in Southern California, a magnitude 7.3, which was followed within hours by increased seismicity at locations across the western United States, some of them more than 1,000 kilometers away. It has been documented repeatedly since. Geothermal fields and volcanic regions are especially susceptible, probably because fluids in the crust make faults there easier to perturb, but dynamic triggering has strict limits of its own. It is weak. It acts almost exclusively on faults that were already critically stressed, meaning it does not create readiness. It only caches in readiness that already existed. Its effects are usually observed within minutes to a few days, and critically, it does not change the long-term probability of a large earthquake in the triggered region. A fault that gets nudged over the edge by a passing wave was going to fail soon regardless. The wave changed the timing by a small amount, not the outcome. So what do we conclude about the eastward events? For Nicaragua, at 700 kilometers on the same subduction system, a genuine but weak relationship is plausible. That region also produces magnitude 4 and 5 earthquakes on its own regularly, so a magnitude 4.7 there on any given day is not remarkable. I would call it possible and unproven. For the Cayman Islands, at 2,000 kilometers on an entirely different plate boundary, coincidence is by far the most likely explanation. The Cayman Trough is seismically active in its own right. A magnitude 5.1 there is a normal occurrence. If you look at any 2-day window in the past year, you will find events of comparable size somewhere along that boundary. And yet, I do not want to be dismissive about the instinct behind the observation, because the instinct is sound even if the specific causal claim is unlikely. Watching the Caribbean plate after a large earthquake near the Triple Junction is a reasonable thing to do, for a reason that has nothing to do with stress transfer. It is reasonable because the Caribbean boundary is genuinely dangerous, genuinely under-monitored compared to the Pacific margin, and genuinely capable of killing an enormous number of people. If a magnitude 5.1 there prompts someone to look more closely at a fault system that most people have never heard of, that is a good outcome regardless of whether the earthquake had anything to do with Mexico. There is also a version of the observation that survives the physics entirely, and it is the more interesting version. The Chiapas sequence and the Caribbean boundary are not causally linked by a magnitude 7.3. They are linked by the fact that they are both being driven by the same larger machine. The Cocos plate pushing northeast into North America is part of the same regional plate configuration that squeezes the Caribbean plate eastward. These systems are neighbours in a mechanical sense, sharing boundaries, sharing a triple junction, exchanging motion across geological time. They do not need one earthquake to connect them. They were always connected, and in a week where one corner of that system is producing nearly every significant earthquake on Earth, glancing at the rest of the machine is not paranoia. It is just paying attention. So let me show you what is actually over there, because the fault system running east from Guatemala has a history that makes the Chiapas sequence look gentle. Part 8. The Fault That Killed. 23,000. Run your finger east from the Chiapas coast, across the neck of Guatemala, and out into the Caribbean Sea. You're tracing the boundary between the North American plate and the Caribbean plate. Unlike the Middle America Trench, this is not a subduction zone. Nothing is diving underneath anything here. This is a transform boundary, which means the two plates are sliding horizontally past each other, grinding sideways in opposite directions. The Caribbean plate is moving east relative to North America at roughly 20 millimeters per year. That motion is accommodated by a system of left lateral strike-slip faults. On land in Guatemala, the two major players are the Motagua Fault and the Polochic Fault, running roughly east to west across the country. Offshore, the boundary continues into the Cayman Trough, a long, narrow, unusually deep basin, and is carried by the Swan Islands Transform Fault to the west and the Oriente Fault along the southern edge of Cuba to the east. If the mechanics sound familiar, they should. This is essentially the same kind of fault as the San Andreas. Two plates sliding past each other horizontally, storing strain along a locked interface, releasing it in sudden lateral jumps. The difference is that the San Andreas is right lateral, and this system is left lateral, which is a difference in direction, not in kind. On the 4th of February, 1976, at about 3 in the morning local time, the Motagua Fault ruptured. Magnitude 7.5, roughly 230 kilometers of surface rupture, and because it happened at 3 in the morning, when the population of Guatemala was asleep inside adobe and unreinforced masonry homes that could not survive lateral shaking, it killed approximately 23,000 people and injured around 76,000 more. Something in the region of 1 million people were left without shelter. 23,000 deaths from a magnitude 7.5. Now hold that against the earthquake we have been discussing all night. July 17th, magnitude 7.3. A larger release of energy is separated from a smaller one by only 0.2 of a magnitude unit here, and yet the outcomes are not remotely comparable. The Mexican earthquake occurred offshore at depth, with modern building stock along the affected coastline and modern warning systems in place. The Guatemalan earthquake occurred on land, at shallow depth, directly beneath dense, unreinforced housing, in the middle of the night. This is the point that I keep coming back to on this channel, and I will keep coming back to it, because it is the most useful thing anyone can understand about earthquakes. Magnitude does not determine the death toll. Magnitude plus depth, plus distance from people, plus what those people's buildings are made of, plus the time of day, plus how much warning anyone had, determines the death toll. We covered this in detail in our video from July 10th on the earthquake striking Venezuela, Japan and California within the same window, and the pattern held there exactly as it holds here. The country that had prepared survived a comparable earthquake with almost no casualties. The country that had not, did not. Guatemala in 1976 is one of the starkest entries in that entire ledger, which brings me back to the Cayman Islands earthquake from last night, and why I said it was worth watching, even though I do not think Mexico caused it. The Swan Islands Transform and the Oriente Fault are the offshore continuation of the fault system that produced 1976. That system runs directly past the southern coast of Cuba, past Jamaica, past Hispaniola. The 1992 magnitude 7.0 that struck near Puerto Limón in Costa Rica, the 2010 Haiti earthquake that killed well over 100,000 people on a related fault system further east, these are all part of the same broadly interconnected Caribbean plate boundary story. The Haiti earthquake in 2010 deserves a moment on its own, because it is the clearest modern demonstration of what this class of boundary can do. Magnitude 7.0. Shallow, around 13 kilometers, close to Port-au-Prince. Estimates of the death toll vary widely depending on the source, but every credible figure runs into 6 figures, and the physical destruction of the capital was close to total. A magnitude 7.0, 0.2 of a magnitude unit smaller than the July 17th earthquake off Chiapas, which killed nobody. The difference was not the earthquake. The difference was that one of them happened 80 kilometers offshore at depth, and the other happened directly beneath a dense city built largely of unreinforced concrete on ground that amplified the shaking. Same class of fault, same class of magnitude, outcomes separated by 5 orders of magnitude in human cost. A magnitude 5.1 south of Grand Cayman is, by itself, nothing. It is a routine event on an active boundary. It would not have made the news in any other week, but it made the news this week because everyone happened to be looking at that part of the world, and having looked, the useful thing is not to invent a causal link back to Mexico. The useful thing is to notice that this boundary exists, that it has killed more people in the last 50 years than the Middle America Trench has, and that it receives a fraction of the monitoring attention. I said earlier that the Chiapas sequence sits near a triple junction where 3 plates meet. Now you can see why that matters beyond the structural complexity. It means that this one corner of the planet is where a fast subduction zone, a continental transform boundary, and a young oceanic plate all come into contact. It is one of the more mechanically complicated places on the surface of the Earth, and an earthquake sequence spreading across 90 kilometers, with depth scattered across 25 kilometers of vertical range, is exactly what a mechanically complicated place produces when you hit it hard. So the honest summary of the eastward question is this. The stress from July 17th did not travel to the Cayman Islands. It could not have. But the fact that we were all watching when a routine Caribbean earthquake occurred has drawn attention to a fault system that deserves more of it, and that is a reasonable trade. There is one more neighbour worth mentioning before we turn west toward the question in the thumbnail, and it is the one you can actually see from the ground. Part 9. The volcanoes. On the same arc. Everything we have discussed so far happens underwater, or underground, in places no one can look at directly. But the Cocos Plate leaves one signature at the surface that anyone can walk up to, and it sits about 200 kilometers from where these earthquakes are happening. When a slab of oceanic crust descends into the mantle, it carries water with it. Water locked into the minerals of the seafloor, water in the sediments, water bound chemically into the rock. As the slab goes down and heats up, that water is driven out, and when water is introduced into hot mantle rock, it does something counterintuitive. It lowers the melting point. Rock that was solid at a given temperature becomes partially molten simply because water has been added to it. That melt is buoyant, it rises, and where it reaches the surface, you get a chain of volcanoes running parallel to the trench, offset inland by roughly 100 to 200 kilometers, tracing the line where the descending slab hits the right depth to release its water. That is a volcanic arc. And the one built by the Cocos Plate runs the length of Central America. In Guatemala, the arc includes 2 of the most persistently active volcanoes on the planet. Fuego sits southwest of Guatemala City and it barely stops. According to the most recent weekly bulletin from the Smithsonian Global Volcanism Program, published on July 9th, Fuego was producing daily strombolian explosions at rates of 5 to 12 per hour, sending gas and ash plumes as high as 1.1 kilometers above the summit and drifting as far as 40 kilometers. Rumbling was audible from surrounding communities. Santa Maria, further west, hosts the Santiaguito Dome Complex, and the same bulletin described high levels of ongoing activity there, with lava continuing to extrude at the Caliente Dome, incandescence visible at night, and daily avalanches of blocky lava tumbling down the flanks. I want to be careful with these numbers, because that bulletin was published on July 9th, 10 days before the data I've been working from. Those are weekly observations, not real-time confirmations of what those volcanoes are doing tonight. Both of these systems are in near-continuous eruption as a baseline condition, so nothing about that activity is unusual or connected to the earthquakes. Fuego was erupting before the magnitude 7.3, and it will be erupting long after this sequence fades. The reason I bring them up is not to imply a link, it is to make the machine visible. We have spent this video talking about a plate descending at 76 millimeters per year, about strain accumulating on a locked interface, about a slab tearing itself apart under its own weight. All of that is invisible. It happens under kilometers of water and rock, inferred from wiggles on a seismograph. Fuego is the same process, expressed in a form you can see with your eyes from a hillside. Every explosion at that summit is water that came off the Cocos Plate as it went down beneath the exact stretch of seafloor that has been shaking for the past 2 days, driven off at depth, melting the mantle, and rising for tens of thousands of years until it reached the sky. The earthquakes and the volcanoes are 2 outputs of one machine, not connected event to event, but connected at the level of cause. And when you understand that the same subduction that built those volcanoes is what is locked and loading offshore right now, the sequence stops being an abstraction on a map. While we are on volcanoes, let me give you the rest of the monitored world over the same window, because it provides the same kind of baseline that the global earthquake count provided earlier. 6 volcanoes under United States monitoring currently sit at elevated alert levels. Great Sitkin, in the Aleutian Islands, is at watch, with an aviation color code of orange, the highest status on the list, with slow lava effusion continuing to feed a thick flow inside its summit crater and seismicity described as low. Below that, 5 systems sit at advisory with a yellow color code: the Atka Volcanic Complex, Kuprianov, Shishaldin, Kalawia, where episodic fountaining has been continuing at variable levels, and Ahi Seamount, an underwater volcano in the northern Mariana Islands. Further afield, that same July 9th bulletin logged new eruptive activity at Etna in Sicily, with lava effusing from 2 vents and a new fissure opening between craters. Krakatau in Indonesia sat at alert level 3 with an orange aviation code, and Mutnovsky, on the Kamchatka Peninsula, produced an explosion that sent an ash plume 3.5 kilometers above its summit. None of that is connected to Mexico. All of it is the ordinary condition of a planet with somewhere between 40 and 50 volcanoes erupting at any given moment. That machine has been running for millions of years. It will keep running long after everyone watching this is gone. Which is worth remembering when we finally turn to the question that brought most of you here. Because that question is really a question about time, and about how badly humans handle geological time when it intersects with our own. Part 10. Should the West Coast worry? Let me answer the question directly before I explain it, because I think you deserve the answer first and the reasoning second. No. Nothing happening off the coast of Chiapas changes the probability of an earthquake in California, Oregon, or Washington. Not by a measurable amount. Not by an unmeasurable amount. The Mexican sequence cannot load West Coast faults, and if it stopped tomorrow, the West Coast risk picture would be exactly what it was last week. That is the answer. Now here is why, and then here is the part that complicates it, because the complication is the real story. We already did most of the physics in the Caribbean section, so this goes quickly. Static stress transfer from the July 17th rupture reaches perhaps 1 to 200 kilometers. The southern San Andreas is roughly 2,500 kilometers from that epicenter. San Francisco is further, Cascadia is further still. At those distances, the static stress change is not merely small, it is smaller than the daily tidal stress that the Moon exerts on the same faults, and the Moon has been doing that twice a day for 4.5 billion years without triggering anything. Dynamic triggering reaches further, and it did reach California, in the sense that the seismic waves from the magnitude 7.3 physically passed through the state. We know they did, because seismographs across the western United States recorded them. That is not speculation. The instruments logged the arrival. But recording a wave and being affected by a wave are different things. Dynamic triggering from a magnitude 7.3 at 2,500 kilometers produces transient stress changes that are, again, comparable to or smaller than tidal effects. And dynamic triggering, when it does work, produces its effects within minutes to days. It is now more than 2 days. Nothing happened. So the honest verdict on the thumbnail question is that this earthquake was not a trigger. It was a stress test of attention. It made millions of people look at the West Coast who were not looking at it last week. And what those people found when they looked is the actual story. Because the West Coast situation is genuinely serious. And it was genuinely serious before any of this, and it will be genuinely serious next month when the Chiapas sequence has faded from the news entirely. Here is what is independently true, with no connection to Mexico whatsoever. Research published this year in the Journal of Geophysical Research Solid Earth, led by Burkhard, with co-authors from the University of Bern and the United States Geological Survey, reconstructed the stress history of the southern San Andreas and San Jacinto fault systems over the past millennium. The finding was that these faults are currently carrying more accumulated stress than at any point in the last 1,000 years. Not more than last decade. Not more than since we started measuring. More than at any point in a reconstruction that runs back 1,000 years. The study focused particular attention on a structure called the Cajun Pass, where the San Andreas and the San Jacinto come into close proximity northeast of San Bernardino. Cajun Pass functions as what seismologists call an earthquake gate. It is a structural complexity in the fault geometry, and complexities like that can either stop a rupture in its tracks or let it through. If a rupture starting on one of those faults arrives at Cajun Pass and is stopped, you get a moderate to large earthquake confined to one segment. If it passes through the gate and continues onto the other fault system, you get a joint rupture, and the modelling for that scenario produces earthquakes in the magnitude 7.4 to 7.8 range, propagating directly into the Los Angeles basin. The San Bernardino segment specifically was found to be carrying around 3.6 megapascals of accumulated stress, the highest value anywhere in the 1,000-year reconstruction, exceeding even the peak recorded about 50 years ago. Now put a clock on it. The southern San Andreas has not produced a major rupture since 1857, when the Fort Tejon earthquake, estimated at around magnitude 7.9, tore roughly 360 kilometers of fault from Parkfield down towards San Bernardino. That was 169 years ago. The average recurrence interval on that section, based on paleoseismic trenching, sits somewhere in the range of 1 to 2 centuries, so 169 years is not overdue in the sense of a bus being late. Earthquake recurrence is not periodic, and treating it as a schedule is a category error. But it does mean that we are well inside the window in which the historical record says these things happen, on a fault that measurement now says is more loaded than it has been in 1,000 years. That is the southern half of the state. The northern half has its own situation, and it is stranger. The San Francisco Bay Area has gone quiet. I mean that in a specific technical sense. When you look at the seismicity map for Northern California on any given day, you normally see a scatter of small earthquakes distributed along the San Andreas, the Hayward Fault, the Calaveras, the Rogers Creek. Small events, magnitude 1, magnitude 2, occasionally a magnitude 3. That is the background hum of a plate boundary doing its business. Right now there is activity to the north of the Bay Area, and there is activity to the south of the Bay Area, and there is a dead zone in between where almost nothing is happening. The observer watching this on the night of July 18th put it bluntly. His words, more or less, were that he honestly did not know what was going on there, that it was super quiet, that he was really shocked, and that he did not think it was a good sign. Now, I want to handle this carefully, because seismic quiescence is one of the most seductive and most frequently misread signals in this entire field. The seductive reading goes like this. A locked fault produces fewer small earthquakes precisely because it is locked. Stress accumulates without release. The quiet is not the absence of danger, the quiet is the danger, accumulating silently. And there are documented cases in the literature of quiescence preceding large earthquakes. The problem with that reading is the same problem we ran into with foreshocks. Quiescence is extremely common, and large earthquakes are extremely rare, so the overwhelming majority of quiet periods are followed by more quiet periods. There is no established, validated method for using seismic quiet to forecast anything. Some studies have found the signal, others have looked for it and not found it, and it has never crossed the threshold into operational use. So the correct thing to say about the Bay Area quiet is that it is real, that it is noticeable, that it means something is not currently slipping across a segment that historically does slip, and that nobody can tell you what that implies about timing. What the quiet does mean, unambiguously, is that strain is not being released there. The plate motion has not stopped. The Pacific plate is still moving northwest relative to North America at about 50 millimeters per year, every day, without interruption. If that motion is not being accommodated by small earthquakes, and it is not being accommodated by aseismic creep, then it is being stored. The Bay Area's last two major earthquakes were 1989, the magnitude 6.9 Loma Prieta event in the Santa Cruz Mountains, and 1906, the magnitude 7.9 that destroyed San Francisco. The Hayward Fault, which runs directly beneath Oakland, Berkeley and Fremont, last ruptured in 1868, and is considered one of the most dangerous faults in the United States, purely because of what sits on top of it. None of that is new information. All of it was true yesterday, and the day before, and in 2017 when Tehuantepec happened, and in 2011 when Tohoku happened. Which brings me to what I actually think the answer to the thumbnail question is, and it is not quite yes and it is not quite no. Should the West Coast worry about the Mexico aftershocks? No. There is no mechanism. The connection does not exist. Should the West Coast worry? That is a different question with a different answer, and the answer has been the same for decades. Yes, in the specific sense that preparation is warranted and consistently neglected. Not because of anything happening in Chiapas, because of what is sitting underneath Southern California at a 1,000-year stress maximum, and what is not moving underneath San Francisco Bay. The Mexican earthquake did not create any of that. It just turned the lights on in a room that was already full. Part 11. What is actually underneath California? I want to spend a little more time on this, because I think the West Coast question deserves better than a paragraph, and because there is a way of thinking about it that I find genuinely clarifying. Everyone knows California has earthquakes. What most people do not have is a mental model of why California has the specific kind of earthquakes it has, and that model changes how the numbers land. California is not a subduction zone. That is the first thing to internalize, and it explains almost everything downstream. In Mexico, in Japan, in Chile, in Alaska, one plate is diving beneath another, and that geometry allows for enormous locked areas and therefore enormous earthquakes. Magnitude 9 is available at a subduction zone. Most of California is a transform boundary. The Pacific Plate and the North American Plate are sliding past each other horizontally along the San Andreas system. There is no plate diving under anything through most of the state, which means there is no vast, gently sloping locked surface thousands of square kilometers across. There is a more or less vertical fault plane extending down perhaps 15 to 20 kilometers to where the rock becomes too hot and ductile to store elastic strain. That geometry puts a ceiling on the magnitude. To get a magnitude 8 on a strike-slip fault, you need to rupture an enormous length of it, because you cannot get the area from depth. The 1857 Fort Tejon event managed roughly 360 kilometers and came out around magnitude 7.9. That is close to the practical maximum for the San Andreas, which sounds reassuring until you look at where the fault runs. A magnitude 7.9 on a subduction interface, 100 kilometers offshore, at 40 kilometers depth, is a serious event that mostly threatens through tsunami. A magnitude 7.8 on a strike-slip fault running through the Inland Empire at 10 kilometers depth, directly beneath freeway corridors and aqueducts and 20 million people, is a fundamentally different kind of problem. The energy is lower, the proximity is catastrophic. This is the same arithmetic we ran on Guatemala in 1976. A magnitude 7.5 on land at shallow depth beneath vulnerable housing killed 23,000 people. A larger magnitude offshore killed a fraction of that. Depth and location dominate, and it is why the Cajun Pass finding matters so much. That gate sits at the northern end of the San Bernardino segment, which is the segment carrying the highest stress in the entire 1,000-year reconstruction, and it is the structure that determines whether a rupture stays confined or runs south into the most densely populated corridor in the western United States. Now let me connect this back to why we are here tonight, because I do not want this to become a separate video about California when the subject is Mexico. The reason these two stories touch at all is a single physical concept, and we have now used it 3 times. Stress transfer. It is the mechanism by which one earthquake can influence another, and the entire question of whether Chiapas matters to California, whether Chiapas matters to the Cayman Islands, whether Chiapas matters to the next segment of its own trench, is a question about how far and how strongly that mechanism reaches. The answer is that it reaches strongly for tens of kilometers, weakly for hundreds, and effectively not at all for thousands, which means the honest map of concern looks like this. The section of the Middle America Trench immediately adjacent to the July 17th rupture, along strike to the northwest and southeast, has genuinely had its stress state altered by that event. That is real. That is measurable. That is why the aftershock zone spreads across 90 kilometers rather than sitting on a point. Everything beyond that is decoupled, and once you understand that, a lot of the noise around earthquakes resolves itself. Every time a large earthquake happens anywhere on the Pacific Rim, a wave of speculation follows about whether it will set off the next one somewhere else. That speculation almost always fails the distance test, and it fails it by 2 or 3 orders of magnitude. The plates around the Pacific are not a chain of dominoes. They are mechanically independent systems that happen to encircle the same ocean, and the reason they seem to act together is that we watch them together. We went through this in detail in our video from July 10th, looking at Venezuela and Japan and California producing significant earthquakes within the same window and asking whether the planet was somehow waking up. The answer then was that global earthquake rates were running at their ordinary long-term baseline, that roughly 120 to 140 magnitude 6 events occur every year regardless of how it feels, and that what had clustered was the coverage rather than the geology. That same answer applies tonight, with one adjustment. Tonight the clustering is real in one specific place. It is real in a 90-kilometer box off Chiapas. It is not real anywhere else on the map. There is one more thread I want to pull before we look at what the instruments were actually showing on the west coast last night, and it concerns the way we talk about the Cascadia subduction zone, because Cascadia is the one place in the United States where the Mexican comparison genuinely does apply mechanically. Cascadia is a subduction zone. The Juan de Fuca Plate, a fragment of oceanic crust, is descending beneath North America off the coast of Northern California, Oregon, Washington, and Vancouver Island. It is the same class of system as the Middle America Trench, capable of the same class of earthquake, and it last ruptured its full length on the 26th of January, 1700, in an event estimated between magnitude 8.7 and 9.2, 326 years ago. We covered the current state of that system in our video from July 15th, when tremor counts along the margin jumped to 307 epicenters spread across the full length of the subduction zone, rather than clustering in one segment. Tremor is not an earthquake, and it cannot predict one. But the slow slip that produces tremor happens down dip of the locked zone, and every episode of it transfers a small increment of additional load onto the locked section above. So if you want a genuine mechanical analogue to what is happening off Mexico right now, it is not the San Andreas, it is Cascadia. Same geometry, same physics, same class of maximum event. The difference is that Chiapas released a magnitude 7.32 days ago and is now working through the consequences, while Cascadia has released nothing for 326 years and continues to say very little. Which of those two situations should concern you more is, I think, a question that answers itself. And there is one final asymmetry between them that I want to leave you with, because it reframes how the Mexican sequence should be read. Off Chiapas, the system is talking, loudly. 8 events in 9 hours, spread across 90 kilometers, catalogued and published within minutes of occurring. Whatever is happening there, we can watch it happen. Off the coast of Oregon, the system says almost nothing. The locked zone at Cascadia produces very few earthquakes, precisely because it is locked. The interface is not slipping, so it is not generating the small events that would tell us where the stress is concentrating. The most informative signal we get from it is tremor, which happens well below the locked zone, and only tells us about the part of the fault that is already sliding freely. So the place that is making noise is the place we can monitor, and the place that is silent is the place carrying 326 years of accumulated strain. That is an uncomfortable inversion, and it is worth sitting with when you decide where your attention is best spent. The Mexican sequence deserves watching, because it is doing something slightly unusual and we can see it. Cascadia deserves preparation because it is doing nothing at all and we cannot. Part 12. The Small Signals. So what were the instruments on the West Coast actually showing while all of this was happening in Mexico? Because there is a difference between the long-term stress picture we just walked through and what a person watching the map on a Saturday night was literally looking at. Here is the list, and I want to go through it carefully, because at least one item on it is going to look alarming and is not, and I would rather you hear the explanation from me than from someone with a more excitable presentation style. First, a magnitude 2.8 on the Gorda Ridge, off the coast of Northern California, within about 90 minutes of the observation being made. The Gorda Ridge is a spreading centre. It is the opposite of a subduction zone. It is where new seafloor is being manufactured, where the crust is pulling apart and magma is rising to fill the gap. The Gorda Plate, a small fragment of oceanic crust squeezed between much larger neighbours, is being created along that ridge and consumed at the southern end of the Cascadia subduction zone. Earthquakes on a spreading ridge are common, they are shallow, and they are generally small, because the crust there is thin, hot, and cannot store much elastic strain before it fails. A magnitude 2.8 on the Gorda Ridge is entirely routine. The observation attached to it was more interesting than the event itself. The reasoning offered was that activity on the Gorda Ridge could be adding stress to the southern end of the Cascadia zone, which is mechanically reasonable. The Gorda Plate is the piece being subducted at southern Cascadia, so what happens to that plate at its western edge does eventually propagate to its eastern edge. The scale of that transfer from a magnitude 2.8 is essentially negligible, but the geometry of the reasoning is sound. Second, the Cascadia tremor count, 37, in a tally compiled at around 6 in the evening local time. I want to put that number in context because it will otherwise mean nothing. In our video from July 15th, we discussed a day when that same tracker logged 307 tremor epicenters spread across the entire margin. 37 is a quiet day by comparison. Tremor counts fluctuate enormously depending on where the system is in its slow slip cycle, and a low count simply means no episode is currently in progress along the monitored segments. The important caveat is one the observer flagged himself. That tally was compiled before the Gorda Ridge event, Any response, if there were to be one, would not appear until the following evening's update, so the honest status is that we do not yet know, and the next update is the first place to look. Third, and this is the one that needs unpacking, a magnitude 2.3 near Willows in Glenn County, Northern California, catalogued at 19 miles depth. 19 miles is about 31 kilometers. For an earthquake in the Northern California interior, well east of the coast, that is unusually far down, and the observer immediately flagged it as suspicious for a specific reason. The Cascadia subduction zone does not extend that far south. There is no descending slab beneath Glenn County to host an earthquake at that depth. He also checked the review status, found the event was still under automatic processing, and predicted the depth would be revised shallower once a human seismologist looked at it. That is exactly the right call, and it is the same issue we spent time on earlier in this video. Automatic solutions are machine output. They are fast, they are usually approximately correct, and they are frequently wrong on depth in precisely the way that generates alarming-looking entries. A revision downward would be the unremarkable outcome, and it is the most likely one. Fourth, in the same area, a magnitude 3.1 earlier that evening, along with a general uptick in small events, in the Clear Lake volcanic field. Now, the words volcanic field attached to an earthquake swarm is exactly the kind of combination that generates panic in a headline. So let me be extremely clear about what is happening there, and I am going to quote the observer's own assessment because he handled it correctly and immediately. This is not a volcano getting ready to blow. The Clear Lake volcanic field hosts one of the largest geothermal power complexes in the world, an area known as the geysers. Somewhere in the region of 15 to 20 power plants operate there. The way the technology works is that water is injected into hot rock at depth, flashed into steam by the natural heat of the system, and that steam is brought back to the surface to spin turbines and generate electricity for a substantial slice of Northern California. And injecting fluid into rock causes earthquakes. This is not a suspicion, it is not a controversy, and it is not hidden. It is a thoroughly documented phenomenon called induced seismicity, and the geysers field is one of the most studied examples of it anywhere on the planet. Injecting fluid changes the pore pressure in the rock, which reduces the effective friction holding faults closed, which allows small faults to slip that otherwise would not have. The field produces thousands of small earthquakes every year. Magnitude 2 and magnitude 3 events there are entirely routine and are directly attributable to the operation of the plants. I bring this up not to dismiss it, but because it is genuinely one of the more interesting things on the list. Human beings really do cause earthquakes. We do it through geothermal operations, through wastewater injection associated with oil and gas production, through the filling of large reservoirs behind dams. In our video from July 17th, we looked at a magnitude 3.9 off the coast of Florida that turned out to be a naval explosive test rather than an earthquake at all, and the theme is the same. Some of what appears on a seismic map is us. But the scale matters enormously. Induced seismicity in a geothermal field produces magnitude 2 and 3 events, occasionally reaching into the 4s in the most active injection regions. It does not produce magnitude 7.3 ruptures on a subduction interface 80 kilometers offshore. The energy involved in the Mexican earthquake is on the order of 100 megatons of explosive equivalent, released along a fault surface tens of kilometers long, at depth, in the middle of the ocean. There is no drilling operation, no injection well, and no weapon that delivers that. Fifth, movement along the creeping section of the San Andreas. The creeping section runs roughly from Parkfield northwest toward Hollister, and it is the one part of the San Andreas that does not lock. Instead of storing strain and releasing it in large earthquakes, it slides more or less continuously, accompanied by a steady drizzle of small events. It is the exception that proves the rule about locked faults, and the reason it creeps is thought to involve the presence of talc and other weak minerals in the fault zone that reduce friction dramatically. Activity there is normal. It is what that segment does. The observation that it indicates the plate is adjusting is fair enough as a general statement. Sixth, a magnitude 2.3 and several smaller events on the Malibu Coast Fault in Southern California, along with continued microquake activity in the San Jacinto Fault Zone. The San Jacinto is the fault system that shares the Cajon Pass Gate with the San Andreas, and it is one of the two systems identified in that 1,000-year stress reconstruction. So small events there are worth noting, and the observer's characterization was that the whole area is well stressed and could produce large earthquakes at any time. That is true, and it is true in a way that is easy to misinterpret. Southern California could produce a large earthquake at any time. It could have done so yesterday. It could do so while you're watching this. That has been the standing condition of the region for the entire history of the state, and small events on the San Jacinto do not move that probability meaningfully in either direction, because that fault produces small events constantly. And seventh, a magnitude 3.6 outside Las Vegas early on July 18th. Nevada is riddled with active faults associated with basin and range extension and the Walker Lane belt, and magnitude 3 events there are unremarkable. Add all of that together, and you get a picture of a West Coast that was, on the night of July 18th, doing almost exactly what it always does. A spreading ridge spreading, a geothermal field generating induced earthquakes, a creeping fault creeping, microquakes on stressed southern faults, one suspicious automatic depth solution that will probably be revised, and a silence over San Francisco Bay that nobody can explain and nobody can interpret. Meanwhile, 2,500 kilometers to the south, one small box of seafloor was producing nearly every significant earthquake on the planet. Part 13. Everything else. The planet did. I want to give you the rest of the global picture, because I have spent this entire video telling you the Chiapas cluster stands out, and a claim like that is worthless unless you can see what it is standing out against. So here is the baseline. Here is what the rest of the Earth was doing over the same window. The largest earthquake anywhere outside the Chiapas sequence was a magnitude 5.5 2 kilometers west-southwest of Secaya, in central Peru, at 24 minutes past 2 on the morning of July 19th, at a depth of 10 kilometers. And I want to stop on this one, because in terms of what actually matters to human beings, this may be the most consequential earthquake in the entire dataset. The survey assigns impact alert levels to earthquakes using a system called PAGER, which estimates likely casualties and economic losses by combining the shaking intensity with population data and local building vulnerability. Green means minimal expected impact. Yellow means some casualties or damage are likely. Orange and red escalate from there. Every single earthquake in the current global catalogue is green. Every one, including the magnitude 5.7 off Chiapas, including the magnitude 5.5 in the Scotia Sea, including everything else, except Peru. The Secaya earthquake carries a yellow alert. Why? Not because it was large. It was smaller than the Chiapas event. It is yellow because it was shallow, at 10 kilometers, and because it occurred directly beneath populated terrain in the Peruvian highlands, where a great deal of housing is adobe or unreinforced masonry, which performs very badly under lateral shaking. That is the entire lesson of this channel in one comparison. A magnitude 5.7 offshore in Mexico gets a green alert. A magnitude 5.5 beneath a valley in Peru gets a yellow one. The smaller earthquake is the more dangerous earthquake because of where it happened and what was standing on top of it. Moving on, a magnitude 5.5 in the Scotia Sea between South America and Antarctica at 10 kilometers depth, green alert. This is the South Sandwich and Scotia Arc region we have looked at before, a remote subduction system that produces significant earthquakes regularly and threatens almost nobody directly because there is nobody there. A magnitude 5.3 off the east coast of Kamchatka at a depth of 5.4 kilometers. That depth is worth flagging. 5 kilometers is exceptionally shallow, even by the standards of a subduction margin, and shallow events transmit shaking much more efficiently to the surface than deeper ones. Kamchatka has been producing aftershocks for a year following the magnitude 8.8 that struck there in July of 2025. Then a set of much further down events. A magnitude 4.6 in the Kuril Islands, catalogued between 113 and 140 kilometers depth. A magnitude 4.8 beneath Halmahera in Indonesia at 223 kilometers. A magnitude 4.8 in the South Sandwich Islands region at 122 kilometers. The observer noted 2 additional magnitude 4 events on the backside of Japan at considerable depth, and offered an interpretation I think is worth relaying because it reflects how experienced watchers read these patterns. Deep activity in a subduction system is a sign that the slab is being driven further beneath the region, and the suggestion was to watch the areas up dip of that deep activity where stress accumulates. The Nankai Trough, the Japan Trench, the Taiwan region. I would add a caveat to that. Deep earthquakes in subducting slabs are a permanent feature of every mature subduction zone. They happen continuously, all the way down to about 700 kilometers, which is the deepest earthquakes ever recorded, and the point below which the slab loses the ability to fail brittly at all. Their relationship to shallow megathrust behavior is not established, so watching is fine, inferring is not. Elsewhere, a magnitude 4.9 in western Iran and a magnitude 4.8 on the Iran-Iraq border region, both at 10 kilometers, both within a minute of each other, which almost certainly means they are two solutions for the same event, or a main shock with an immediate aftershock. A magnitude 4.8 south of Java at 10 kilometers, a magnitude 4.9 on the southern East Pacific rise, a magnitude 4.5 in Nepal northeast of Tulsipur, a magnitude 4.6 east-southeast of Hihifo in Tonga, a magnitude 4.5 in Pakistan, a magnitude 4.7 northwest of Australia. The Philippines continued producing magnitude 4 and 5 events, as aftershocks of the magnitude 7.8 that struck there several weeks ago. The Java Trench remained active. New Zealand's South Island produced a magnitude 3, part of what the observer described as several days of increased activity without anything large. Two magnitude 5.5 events in South America drew a comment worth repeating, which was to watch the region between them, on the reasoning that stress concentrates in the gap between two ruptures. That is a real concept, and it maps onto something seismologists take seriously, the idea of a seismic gap. Segments of a fault system that have not ruptured while their neighbours have are, in principle, more likely to be next. The theory has a mixed track record in practice, but it is not fringe. And then two entries I want to end this section on because they are the control group. Yellowstone produced an earthquake swarm in the last couple of days, and then it stopped. Nothing in the preceding 24 hours. The observer's summary was that this is typical Yellowstone behaviour. A swarm appears out of nowhere, runs for an hour or two, and shuts down. That is what a sequence looks like when it genuinely is nothing. It starts, it does not escalate, it does not spread, and it ends. Yellowstone does this constantly, and the overwhelming majority of the time it means the hydrothermal system moved some fluid around and nothing more. Hold that shape in your mind and compare it to Chiapas. Chiapas started, it did not stop. On day 2, it produced its largest event yet, across a 90-kilometre footprint, with depth scattered across 25 kilometres of vertical range, while simultaneously supplying nearly every new significant earthquake on the global count. And a magnitude 1.8 in the New Madrid seismic zone in the central United States, which is a reminder that the most dangerous fault system in America by some measures is not on either coast and produces almost nothing most weeks. New Madrid is worth 10 seconds of your attention even at magnitude 1.8, because it is the strangest entry in American seismology. Between December of 1811 and February of 1812, that zone produced 3 main shocks estimated in the range of magnitude 7.3 to 7.5 in the middle of the North American continent, thousands of kilometres from any plate boundary. The shaking was felt across most of the eastern United States. Church bells were reportedly rung by it in cities hundreds of miles away. Nobody fully agrees on why an intraplate zone that far from a boundary produces earthquakes of that size, and because the crust of the central United States is old, cold, and structurally intact, seismic waves travel through it with far less attenuation than they do through the fractured crust of California. An earthquake there affects an area many times larger than an equivalent event on the West Coast. So a magnitude 1.8 in New Madrid is not a warning of anything. It is just a reminder that the fault systems most people worry about are not always the fault systems that deserve it. There is one more item worth flagging, and it is a data problem rather than an earthquake. The tsunami feed contains exactly one entry, a product for the coast of Chiapas, positioned at 14.4 degrees north and 93 degrees west, essentially on top of our sequence. It has an empty summary field, and it was last updated at 56 minutes past 2 in the afternoon, Universal Time, on July 17th. That is roughly 26 hours before the magnitude 5.7 that started the burst we have been discussing. I want to be completely unambiguous about this. That is not an active tsunami warning. It is almost certainly an orphaned record associated with the July 17th main shock, whose tsunami threat was evaluated at around half a foot and formally stood down. An empty summary field is the classic signature of a stale entry that a feed never cleared. No earthquake in either agency's catalogue currently carries a tsunami flag. I raise it only because I know that if I do not, someone will find it, screenshot it, and post it as evidence that a warning is being suppressed. It is not. It is a piece of automated housekeeping that nobody got around to, sitting at coordinates that happened to have become interesting a day after the record was written. That coincidence is genuinely odd to look at. It is not evidence of anything. That is the world, over the same 2 days. Ordinary. Busy in the way it is always busy. One yellow alert in Peru for the smallest reason and the most human one, and one box of ocean floor off Chiapas doing something that does not quite fit. Part 14. The sun was asleep, and something was still ringing. There is a theory that comes up every single time an earthquake sequence gets attention, and I want to address it properly rather than waving it away, because tonight the data happens to give us an unusually clean test of it. The theory is that solar activity triggers earthquakes, flares, coronal mass ejections, geomagnetic storms, the electric currents they induce in the ground, somehow coupling into the crust and nudging faults over the edge. It is an appealing idea. It has the shape of a good idea. 2 large, dramatic natural systems, one obviously affecting the other, a hidden connection that the establishment supposedly refuses to investigate. And it is not entirely without a physical basis worth discussing, which is why it persists. Geomagnetic storms genuinely do induce electric currents and conductive materials at the surface. That is why they damage power grids and pipelines, and we have covered grid vulnerability on this channel before, so let us test it against tonight, over the exact window in which one patch of seafloor produced nearly every significant earthquake on Earth. Here is what the sun was doing. Nothing. I want to be more specific than that, because the specificity is the whole point. The current NOAA space weather scales read G0, S0 and R0. That is the bottom of every scale. No geomagnetic storm, no solar radiation storm, no radio blackout. The peak planetary K index over the past 24 hours was 1.33 on a scale that runs to 9. The most recent observed value was 1.0. The forecast maximum through July 21st is 2.0. For context, you need a K index of 5 before anything is classified as a storm at all. Solar wind speed was 291 km per second at 1:30 in the afternoon. Universal time. That is background. Slow. The interplanetary magnetic field strength was 4 nanotesla, which is weak, and the north-south component of that field, the BES, was sitting at approximately 0, and assessed as northward, meaning not geo-effective. A northward BES is the closed door of space weather. When the field points north, it does not couple efficiently with Earth's magnetosphere, and energy transfer is minimal. Aurora hemispheric power was 15 gigawatts in the northern hemisphere and 16 in the southern, both below the roughly 20 gigawatt threshold that marks the quiet baseline. X-ray output from the sun was at B8.2, which is low-level background. The peak over the previous 24 hours reached only C1.6. The most recent catalogued flare was a C1.5, and there were no Earth-directed coronal mass ejections observed in any available coronagraph imagery. So during the most seismically concentrated window this planet has seen in a week, the sun was as quiet as it gets. If solar activity drove earthquakes in any meaningful way, this should have been one of the quietest seismic periods of the year. Instead, it produced 144 events above magnitude 4.5 globally and a swarm off Chiapas that we have spent 2 hours discussing. That is not proof of absence. One clean test does not settle a question, but it is a data point that runs directly against the theory on the specific days the theory would need to explain, and I think that is worth more than 1,000 words of argument. Now, having said the sun was quiet, I want to complicate it slightly, because there is a lovely detail in this data, and it makes a point I care about. There has been an alarm ringing continuously since July 17th. The Space Weather Prediction Center has had a continued alert in effect for greater than 2 mega electron-volt-electron integral flux, exceeding 1,000 particle flux units. It was first issued at 50 minutes past 5 in the evening, Universal Time, on July 17th, and it has now been extended twice, running through 3 consecutive serial numbers. The maximum recorded on July 18th was 1,170 particle flux units. The maximum cited when the alert was first issued was 1,382. So every headline metric says nothing is happening, and an alarm has been going off for more than 2 days. What is that alarm actually about? High-energy electrons in the outer radiation belt. When their flux rises above about 1,000 units, they begin to penetrate the outer surfaces of satellites and accumulate charge inside insulating materials, in the body of the spacecraft rather than on its skin. That is called deep dielectric charging, and if enough charge builds up, it discharges internally, which can damage electronics or corrupt commands. Satellite operators take this seriously. It has been implicated in a number of spacecraft anomalies over the years. What it is not is a threat to anyone on the ground. It is not a radiation storm, it is not a geomagnetic storm. The proton flux, which is what actually matters for radiation storms, is sitting at background, around 0.2 units against a threshold of 10. I include it because it makes a point that applies to this entire video. Quiet is not the same as nothing happening. The space environment tonight is quiet by every measure a general audience would recognize, and there is still a genuine ongoing alert affecting real hardware in orbit that almost nobody outside of satellite operations knows about. That is also, in a smaller way, the situation off Chiapas. From the outside, it looks like an ordinary aftershock sequence. Read the numbers closely and something is running slightly hot. And there is one more solar detail worth carrying forward, because it is a thread for the days ahead rather than tonight. There are 4 numbered active regions on the solar disk right now. The most interesting is region 4492, which has only just rotated onto the eastern limb at 15 degrees north, 73 degrees east. It covers an area of 230 millionths of a solar hemisphere with 3 spots, and it currently carries a 35% chance of producing a C-class flare, 5% for an M-class, and 1% for an X-class. Those are the highest probabilities on the disk, and we are seeing that region nearly edge on. The observation from the night of July 18th added useful colour to that. This is a region that was on the Earth-facing side a couple of weeks ago, where it produced an X-class flare and multiple M-class flares, then grew to substantial size while it was around the far side, then weakened considerably before rotating back into view. And behind it, roughly a day further around, there is a second region that appears larger and more magnetically complex. There is also a lengthy coronal hole on the disk that appears to be widening. Coronal holes are regions where the magnetic field opens out into space rather than looping back down, allowing solar wind to escape at much higher speeds. When a coronal hole rotates into an Earth-facing position, the fast stream it emits can arrive a few days later and produce minor to moderate geomagnetic storming. So the Sun is quiet tonight, and it has 2 active regions rotating toward us and a widening hole in its corona. That will matter in the coming days. It will not, however, matter to the earthquakes. And the reason I'm confident saying that is not stubbornness. It is that the energy budget makes the comparison absurd. The magnitude 7.3 off Chiapas released energy on the order of 100 megatons of explosive equivalent. That energy was not delivered to the fault. It was already stored in the fault, accumulated over decades or centuries of plate motion at 76 millimeters per year, held in the elastic deformation of an entire coastal region. A geomagnetic storm induces currents in the ground measured in fractions of a volt per kilometer. The gap between those 2 quantities is not a matter of degree. It is a matter of many orders of magnitude, and no amount of enthusiasm closes it. The Sun did not cause these earthquakes. Nothing above the surface caused these earthquakes. What caused them is a slab of ocean floor sinking into the mantle under its own weight, and the only genuine question left is what part of that slab is currently breaking. Part 15. What comes next? Let me pull all of this back together, because we have covered a great deal of ground, and I want to leave you with something you can actually carry. 2 days ago, a magnitude 7.3 ruptured the Middle America Trench, and everything about the first 24 hours was textbook. A magnitude 6.0 aftershock at 30 minutes, exactly where Both's law says it should be. A run of magnitude 5s. A small tsunami, measured and stood down. The assessment that this was an ordinary sequence was correct on the evidence available, and if you had told me on July 17th that this would be a routine story, I would have agreed with you. Then the sequence stopped following the script. Across 9 hours it produced at least 8 events above magnitude 4.5, 3 of them above magnitude 5.3, and its largest event to date arrived on day 2 rather than day 1. That one box of seafloor, 90 kilometers across, accounted for essentially the entire increase in the global count of significant earthquakes this week. And when we went looking for the measurement that would tell us what that means, we found that the measurement is in dispute. The survey says the largest event of the burst happened 10 kilometers down. The European Centre says 29. The rest of the sequence scatters from 10 to 35, which is either the signature of a genuinely complicated multi-fault system in a triple junction region, or the signature of a monitoring network trying to measure depth for offshore earthquakes, when every one of its instruments is on the same side of them. Both explanations are entirely plausible. Neither can be ruled out from here. That is the honest situation, and I want to make a case for why that is a more interesting place to end up than a confident answer would have been. We have built something remarkable for watching this planet. Thousands of seismometers on every continent and on the ocean floor. Satellites that measure ground deformation to the millimeter. Catalogues updated within minutes and published openly, for free, to anyone who wants them. 2 independent agencies on 2 continents both tracking the same events and both publishing when they disagree. That machine is one of the genuine achievements of the last century, and its limits are not hidden. The disagreement we spent this video on is not a scandal that someone leaked. It is 2 agencies openly publishing their best estimates of a genuinely hard measurement and letting the discrepancy stand in public where anyone can see it. That is science working exactly as it should, and the limit it reveals is real. 80 kilometers offshore, underwater, with one-sided station coverage, we cannot currently tell the difference between a Megathrust interface and the inside of a descending slab in real time. We will be able to in a week or a month once reviewed solutions publish, but not tonight, and not while it matters most. So what should you actually watch for? The first thing is the threshold, and it was named out loud in public before any of us knew what the sequence would do. Multiple magnitude 6.0 events, not one. The magnitude 6.0 from July 17th was the expected largest aftershock, and it fits the statistics almost perfectly. What would matter is a pattern of them, appearing now on day 3 or 4, when the sequence should be thinning rather than escalating. As of the most recent data available to me, that has not happened. The largest event in the July 18th to 19th burst is a magnitude 5.7, and the maximum magnitude across the burst is held flat rather than climbing. Rate is elevated, magnitude is not escalating. Those 2 facts together are much more consistent with a productive aftershock sequence in a structurally messy corner of the world than with anything more serious, and that is the fairest reading of the evidence tonight. The second thing to watch is the depths. Several of these events are still under automatic status. When human seismologists review them and the corrected solutions publish, the sequence will resolve toward the interface, toward the inside of the slab, or toward genuinely involving both. Each of those answers means something different, and unlike almost everything else in earthquake science, this one has a definite answer that is simply not available yet. The third is whether the eastward activity continues. If more moderate earthquakes appear along the North America and Caribbean boundary, the Cayman Trough, the Swan Islands transform, the Motagua system, then the pattern is worth taking more seriously as a pattern, even though the physics says the magnitude 7.3 cannot have caused it. If that magnitude 5.1 south of Grand Cayman stands alone, it was coincidence, and coincidence is what it almost certainly was. And the fourth, for anyone on the west coast of North America, is the Cascadia tremor count. The tally of 37 was compiled before the Gorda Ridge event. The next evening's update is the first data point that could show anything at all. Now let me say the thing I think actually matters, because I have spent 2 hours on a sequence that will most likely fade quietly into the background within a week, and I want to be honest about why that was worth doing. The reason is not that I think something terrible is imminent off the coast of Chiapas. The evidence does not support that, and I am not going to pretend otherwise to hold your attention. The reason is that this sequence is a very clear demonstration of something we usually only understand in retrospect. Right now, tonight, we are inside the exact epistemic situation that seismologists have been describing for 50 years and that the public has never really absorbed. There is a sequence in progress. It is behaving slightly unusually. The measurement that would tell us whether that matters is unavailable. The statistics say the boring answer is almost certainly correct, and the small number of times in history when the boring answer was wrong, the sequence looked exactly like this one right up until the moment it did not. That was true off the Sanriku coast on the 9th of March, 2011. A magnitude 7.3, an ordinary aftershock sequence, a competent monitoring agency applying the correct statistical treatment, and 2 days later, the seafloor moved and 20,000 people died. Nobody was negligent. The treatment was right. The outcome was catastrophic. Both of those things are permanently true at the same time, and that is not a comfortable thing to sit with, but it is the actual state of the field. So the correct posture is not fear, and it is not dismissal. It is the thing that is genuinely hard for people, which is holding a low probability and a high consequence in your head simultaneously without collapsing into one or the other. Almost certainly nothing, not certainly nothing. And the difference between those two phrases is the entire discipline. The Cocos Plate does not know that we are watching. It has been sliding beneath North America at the speed your fingernails grow for tens of millions of years, and it will keep doing so for tens of millions more, building the volcanoes of Guatemala out of water squeezed from its own rock, loading a locked seam offshore one fingernail width at a time, indifferent to what any of us decide about it tonight. The only thing that changes is what we know, and what we know tonight is that 8 earthquakes in 9 hours came out of a box of seafloor 90 kilometers across, that this was nearly every significant earthquake on Earth this week, and that we cannot yet say how deep they were. Which leaves one question, and it is the one I will be checking first thing in the morning. When the reviewed solutions come in and those depths finally settle, will they land on the interface or inside the slab?